and perpendicular lines. There are quite a few proofs in this section. I want you guys to see a lot more because eventually if you're going to be doing proofs on your own. So I want to make sure that you see a lot of them before you actually do them. Okay, so a couple of theorems, and these, if you think about them, they should just make sense. Okay, first one, and we'll only be able to call it Theorem 3.9. It doesn't have a name, so we'll just call it Theorem 3.9. If two lines are parallel to the same line, then they are parallel to each other. That should make sense. Think of all your streets on your town project. They're all parallel, all five of them. So if two of them are parallel and they're both parallel to the same one, then all three of them are parallel, and so on. All right? Theorem 3.10. If in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So these look like streets to me as well, because if you have the top line perpendicular to this transversal, and you have the bottom line perpendicular to the transversal, then the two of them have to be equal, and you could use corresponding angles, you could use same side interiors, all that kind of thing to prove this. But it should just make sense because it looks like streets in a city. Alright, so let's try, it says proof of theorem 3.10. That's that second theorem on the last slide. So you cannot use theorem 3.10 to prove this. Alright, first step every single time is you copy your givens. Okay, so R is perpendicular to T, S is perpendicular to T. Remember that the upside down T is perpendicular, so you need to remember that. Okay, and then that tells us that there's some things in there. We can't just automatically put a right angle box in those and be done. We have to actually state it. If it's not in the proof, it doesn't exist. Okay, so if R is perpendicular to T, that means angle 1 has to be 90 degrees. And if S is perpendicular to T, that means angle 2 has to be 90 degrees. Because that's what perpendiculars do. They make right angles. So we put definition of perpendicular. Alright, next thing, if we know both of those are 90 degrees, aren't they congruent? So I can just go at it like that. And there's a theorem for this that says all right angles are congruent. It doesn't have a name, so we'll just state it because it's short. But it's all right angles are congruent. Okay, so right now in our picture we have this. Those are corresponding angles in my book. So we can say R is parallel to S because the corresponding angles are congruent. That is the converse of a corresponding angles postulate. You did that in section 3 too. Converses just mean the angles are congruent. That makes the lines parallel. Okay, so the proofs still aren't that difficult. You just don't have a lot of practice with them yet, and we'll get there. Alright, theorem 3.11. In a plane, if a line is perpendicular to one of two parallels, then it's also perpendicular to the other. So it's kind of like theorem 3.10, just a little smidge different. They're saying we already know these are parallel, and then I tell you that the transversal is perpendicular to one of them, then it automatically makes it perpendicular to the other. So kind of like a converse of the other one. Alright, so let's do another one. And this one we're not proving any theorems, so we can use all of them. They're all fair game. Okay? So first step, copy your givens. So A is perpendicular to B, B is perpendicular to C, C is perpendicular to D. All given. Okay, I'm going to go ahead into the picture and put boxes just so we can see things because they don't have angles labeled, so we're not going to be saying that angles are 90 degrees and that sort of thing. Okay, it kind of leads you to what you want to do. So it says A is perpendicular to B, B is perpendicular to C, and C is perpendicular to D. Okay, so you should be able to say, by looking over here at the right side, if one line is perpendicular to two lines, they would have to be parallel then, right? So we can say that B is parallel to D. Well, let's look back here. Which theorem is this? We don't know they're parallel already, so it's not this one. Let's look at this one. If two lines are perpendicular to the same line, then they are parallel to each other. That's theorem 310. So we'll go back in here and we'll put theorem 310. See how sometimes you have to look back at your notes to figure this out? That does happen. Alright, so we know these lines are parallel now. Okay, A is perpendicular to B already. So if it's perpendicular to one of the parallels, what happens if I continue this line down? Wouldn't it have to be perpendicular here as well? Which is what we're trying to prove. So A is perpendicular to D, and if you look back at this theorem, it says if it's perpendicular to one of two parallels, then it's also perpendicular to the other. So that would be theorem 311. There's a lot of theorems here, so if you take good notes, you can use your notes to look back, look things up, put them in your proof, and go on. Alright, one more. And we're not proving any theorems here, so we can use everything. Alright, first step, copy your givens. And then we'll go ahead into the picture and we'll draw these in. So it says L is parallel to K and M is parallel to K. Uh-oh, you should be able to figure this out real quick. Is L parallel to M? Because we have a theorem that says if two lines are parallel to the same line, then they're parallel to each other. Everybody's parallel to everybody. That's theorem 3.9. Okay? Getting more proofs. We're starting to get into this now.